In the last lecture, we were examining the heat transfer correlation for high Peckley number heat transfer for a stagnation point flow. So, I will briefly revise what we did in the last lecture, and I will complete the derivation of the correlation for this stagnation point flow. Okay, this is the flow which is incident on a surface. Okay. And we take the two axes, the streamwise axis parallel to the surface as x and the axis perpendicular to the surface as z, and there is a heated section of length L here. Okay. There is a heated section of length L, and we would like to know the heat transfer correlation for this heated section with temperature Tw in a fluid which is at temperature T infinity far from the surface. Okay. And we define the scaled temperature as T star is equal to T minus T infinity by Tw minus T infinity. Okay. So, in that case this is T star is equal to 0 far away as Z becomes large, and T star is equal to 1 on the surface. Okay. The scale temperature is 1 on the surface and it is 0 far away as T becomes large. The velocity fields, in this case they are given. This is a forced convection problem where the velocity fields are specified. For this stagnation point flow, the velocity fields are Vx is equal to k times x times z, and Vz is equal to minus k z square by 2. Okay. You notice that Vx is positive in the positive x direction. I am calculating the heat transfer correlation for only one half, okay, the right half. Okay. I am calculating the heat transfer correlation only for the right half. Once I calculate the average flux from 0 to L by 2, the average flux on the other side has to be the same. Okay. So, I am only taking the first quadrant in this case, where Vx is positive and Vz is negative. Vz is negative because the fluid is coming towards the surface. So, these are the velocities that are specified, where k has dimension of L inverse T inverse. So, that k times the length square has the same dimension as velocity. Okay. So, k has dimensions of length inverse T inverse. In the previous example, we had the strain rate which had dimension of T inverse. Okay. So, you would expect the Peckley number in this case to be Pe is equal to k L cubed by alpha, where alpha is the thermal diffusivity just on the basis of dimensional analysis. The convection diffusion equation is Vx partial T star by partial x plus Vz partial T star by partial z is equal to alpha partial square T star by partial z square. Okay. Neglecting streamwise diffusion in comparison to cross stream diffusion, because we would expect cross stream diffusion to be dominant in the limit of high Peckley number. And then we substitute the similarity variable z is equal to eta is equal to z by delta x of x. Okay. Substitute that in the velocity components and in the derivatives of the temperature. Okay. If you recall, we had derived the temperature derivatives using chain rule for differentiation. So, in terms of eta, partial T star by partial z is equal to 1 by delta x dt by d eta. Okay. Okay. The second derivative with respect to z was d square 1 by delta x square d square t star by d eta square. Okay. And the derivative with respect to x was obtained by chain rule for differentiation, because delta is a function of x here. Okay. Delta is a function of x. So, you can use that with chain rule for differentiation to determine the x derivative. And I will just write the final result. You can verify that using chain rule for differentiation. Minus eta by delta x d delta x by dx dt by d eta. Okay. So, those were the derivatives that we had obtained. Okay. Substitute that into the conservation equation. So, the first term, the velocity k times x times delta x star eta. Okay. Z is delta x star, I am sorry, z is equal to delta x times eta. Okay, there is no star here, it is just delta x times eta into the derivative with respect to x, okay, the derivative with respect to x, okay, into minus eta by delta x d delta x by dx dt star by d eta. Okay. The second term is the derivative with respect to z. Okay. Vz is negative, as you notice here. Okay. Vz is negative. So, you get minus k delta x square, okay, eta square by 2, okay, that is Vx square, into partial t by partial z, which is 1 by delta x dt star by d eta. Okay. And I have the second derivative with respect to x here. So, I get the thermal diffusivity by delta x square d square t by d eta square. That is the final expression for the temperature equation. Okay. That is the equation expressed in scaled form in terms of the variable eta. Okay. And now, I can multiply throughout by delta x square by alpha, so that the coefficient of the term on the right side becomes 1. Note that both of these terms, okay, are proportional to eta square times dt by d eta. Okay. Both the terms on the left side are proportional to eta square times dt by d eta with a negative sign. So, I can take this out as a common factor, okay, minus eta square dt by d eta, that is a common factor, okay, into this gives me k by alpha is a common factor, okay, of both terms on the left side. When I multiply it by delta x square by alpha, I will get a factor of k by alpha here into, okay, I am getting x, okay, delta x square d delta x by dx plus, okay, delta x plus delta x cubed by 3 by 2, I am sorry. Okay, is equal to d square t star by d eta square. Okay. This admits a similarity solution only if this term is a constant. That constant can have any value. The solution for temperature in terms of eta depends upon the value of this constant. the final temperature in terms of x and z does not depend upon this value of this constant, as we saw for the example of a flat plate. Therefore, without loss of generality, I can consider this constant to be equal to 1. Equation for the temperature becomes minus eta square dt by d eta is equal to d square t okay. That is the equation for the temperature, and you recall this was exactly the same equation that we had for the flow past a flat plate. Okay. This was the same equation that we had for the flow past a flat plate. Okay. So, this is the equation for the temperature, and this can be solved in order to obtain the temperature field. T star is equal to 1 minus 3 power 2 by 3 by gamma of 1/3 okay, times integral 0 to eta d eta prime e power minus eta prime cubed by 3. That was the equation for the temperature in the flow past a flat plate. That equation was determined using the condition boundary conditions. Okay. Okay. T star is equal to 0 at eta is equal to, I am sorry, temperature at the surface is equal to 1. Okay, and T star is equal to 0 for eta going to infinity. Okay. These boundary conditions are the same in this problem as well. T is equal to Tw on the surface. Surface corresponds to eta equal to 0. So, T star is equal to 1 on the surface at eta equal to 0. The temperature T star is 0 far from the surface. Far from the surface, eta is equal to eta tends to infinity. Therefore, the boundary condition is T star is equal to 0 for eta going to infinity. Therefore, the solution that we get for T star in terms of eta is the same as we had for a flat plate. In fact, this solution will be the same for any problem. Okay, the solution will be the same for any problem where the temperature on the surface is the wall temperature, or T star is 1 on the surface, and the coordinate eta is the coordinate perpendicular to the surface, so that the surface corresponds to eta is equal to 0. In that case, for any problem, you will get T star is equal to 1 at eta equal to 0. Far from the surface, eta goes to infinity, okay, and therefore, T star will go to 0 as eta goes to infinity. So, the equation for the temperature in terms of eta and the equation for the boundary and the two boundary conditions are the same when expressed in terms of eta, and therefore, the solution is the same when expressed in terms of eta for any problem for which the velocity decreases to 0 at the surface. Okay. What changes is the dependence of the boundary layer thickness on the streamwise coordinate, okay, which in this case is the x coordinate. Okay. And that has to be determined from the differential equation k by alpha into x delta x square this is equal to 1. Okay. Okay. And I can write this term here, okay. Okay. Delta x square d delta x by, I am sorry, this is x here, I have made a mistake here. The boundary layer thickness varies with the streamwise coordinate, which is in this case is equal to the x coordinate. Okay. This I can write it as 1 by 3 d delta x cubed by dx. Okay. I can write this as 1 by 3 d delta x cubed by dx. Okay. Okay. Therefore, this first term becomes delta x cubed by 3, I am sorry, x by 3 d delta x cubed by dx. Okay. I can rewrite this equation a little. Okay. I can rewrite this equation a little to get a first order differential equation for this variable delta x cubed, okay, for the variable delta x cubed. Okay. I will get d delta x cubed by dx, okay, plus, okay, 3 delta x cubed by 2x is equal to alpha by, okay, 3 alpha by kx. Okay. Multiplying throughout by 3 alpha by kx, this is what I will get. Okay. Now, how do I solve this equation? Okay. This equation is a first order inhomogeneous equation, and there is a general procedure for solving this. Okay. So, I will briefly go through the general procedure for a differential equation of the form, okay, dy by dx plus p of x y is equal to some function q of x. Okay. Okay. You must have seen this earlier. I will just do it briefly so that everybody is on at the same level. Okay. This is done using an integrating factor if, which is defined as e power integral p of x dx. Okay. This is usually written as an indefinite integral, okay, as an antiderivative. Okay. Okay, it is usually written as an antiderivative. Okay. So, then what you do is you multiply the entire equation by the integrating factor, okay, dy by dx e power integral p of x dx plus p of x y e power integral p of x dx is equal to q of x e power integral p of x dx. Okay. And the left side is an expansion of the derivative d by dx of, okay, y times e power integral p of x dx. Okay. Okay. And I can integrate this one time to get y e power integral p of x dx is equal to an integration constant plus integral dx prime between 0 to x, okay, of q of x prime e power integral p of x prime dx prime. Okay. Once again writing it as the antiderivative, not as a definite integral. Okay. Therefore, the solution can be written as y is equal to c by e power integral p of x dx plus 1 by integral, I am sorry, okay. Alternatively, with this definition of the integrating factor, okay, with this definition of the integrating factor, this can be equivalently written as y is equal to c by integrating factor plus 1 by the integrating factor integral 0 to x dx prime q of x prime times the integrating factor expressed in terms of x prime. Okay. So, that is the solution, okay, of this equation by the integrating factor method. Okay. Okay. So, this is just a brief overview of how you solve this equation, and I have spent a little bit of time explaining it here because this method will be used repeatedly during when we are solving boundary layer problems. Okay. So, this is a method that we will use again and again while we are solving these boundary layer problems. Okay. So, in this case the integrating factor is this coefficient. Okay, the integrating factor is the p of x is this coefficient. Therefore, the integrating factor, okay, if is equal to e power integral dx times 3 by 2x. Okay. Okay, that is the integrating factor. So, this is equal to e power 3 by 2 integral dx by x, okay, which is e power 3 by 2 the natural logarithm of x, okay, 3 by 2 times the natural logarithm of x, which will basically be x power 3 by 2, okay, which is x power 3 by 2. Okay. So, then delta x cubed is equal to constant by integrating factor plus integral 0 to x dx prime, okay, times this q of x, which is the right hand side here. This is q of x, which is the right hand side here. Okay. Okay. So, this is x prime power 3 by 2 into 3 alpha by k x prime. Okay. And I should have a 1 over integrating factor outside. Okay. So, okay. So, C constant by integrating factor. Integrating factor in this case is x power 3 by 2. So, constant by integrating factor plus 1 over integrating factor integral 0 to x dx prime times x prime power 3 by 2, that is the integrating factor, and 3 alpha by x, okay, which is take the constants out, 3 alpha by k x power 3 by 2 integral 0 to x dx prime into x prime power half. Okay. Integral of x prime power half is x prime power 3 by 2 divided by 3 by 2. Okay. So, this is equal to into 2 by 3 x power 3 by 2. Okay. X power 3 by 2 divided by 3 by 2 is the integral of x power half. Okay. Okay. So, that is the final solution for the temperature field, for the boundary layer thickness. I am sorry, okay, for the boundary layer thickness, this is the final solution. Okay. How do we determine the constant? Okay. Note that x is equal to 0 is the middle of the stagnation line. Okay. X is equal to 0 is the location of the stagnation line. Okay. At this particular location, the flow is towards the plate. Okay. At this particular location, the flow is coming towards the plate, okay, towards the surface. Therefore, you would expect the boundary layer thickness to be finite at this location. Okay. At x is equal to 0, you would expect that the boundary layer thickness is finite because there is diffusion from the surface, of course, but the fluid flows towards the surface. And because the fluid flow is strong, you would expect the boundary layer thickness to be finite at this location. Okay. The boundary layer thickness delta is finite only if the constant is equal to 0, because you have constant divided by x power 3 by 2. Okay. So, only if the constant is 0 is the boundary layer thickness finite. Therefore, for a finite boundary layer thickness at x is equal to 0, this constant has to be set equal to 0. And from that we simply get that the boundary layer thickness is equal to 2 alpha by k whole power 1/3. Okay. It is a constant. Recall the flow past a flat plate, the boundary layer thickness was increasing proportional to x power half, x power plus half. In this particular case, a stagnation point flow, the boundary layer thickness is a constant. Okay. And from this we can determine what is the flux as a function of x and the average flux. Turns out that the flux as a function of x will be independent of x, because the boundary layer thickness is independent of x. Okay. So, q z at the surface z is equal to 0 is equal to k partial t by partial z at z is equal to 0. Expressed in terms of scaled variables, this is k into t w minus t infinity, okay, by delta x, okay, dt star by d eta at eta is equal to 0. Okay. A negative sign I need to put in both cases, because the heat flux is in the direction of decreasing temperature. Okay. The heat flux is from a higher temperature to a lower temperature. So, it is in the direction of decreasing temperature. So, I have a negative sign. Okay. This is equal to minus k into t w minus t infinity by delta x. This derivative we have already evaluated. This is equal to minus 3 power 2 by 3 by gamma of 1 by 3. Okay. This just emerges from this solution here. Okay. This just emerges from this solution here for the temperature field. Okay. 3 power 2 by 3 by gamma of 1/3. Okay. So, this emerges from this solution for the temperature field. Take the derivative. The derivative of an integral is the value at the upper limit of integration. Okay. In this case, that value is equal to 1. The integrand at the upper limit of integration is equal to 1. Okay. So, it is equal to minus k into t w minus t infinity. Okay. The minus and minus will give me a plus. Okay. Okay. Into 3 power 2 by 3 by gamma of 1/3. Okay. The gamma function I had discussed with you, times 1 over delta, which will basically be k by 2 alpha, okay, whole power 1/3, okay, because delta x is given by this constant value, k by 2 alpha power 1/3. And you can work out the numerical constants here. It turns out that this is equal to this is equal to 0.62 k into t w minus t infinity. Okay. This is the thermal conductivity by alpha by k whole power 1/3. This is the flux at the surface. This is also the average flux, because this flux is now independent of x. Okay. So, therefore, the average flux is equal to the local flux, because the flux is a constant. Okay. Note that this is the parameter in the equation for the velocity field. Okay. So, therefore, the Nusselt number qz at z is equal to 0 by k into t w minus t infinity by L. Okay. So, this will be equal to 0.62 into k L cubed by alpha whole power 1/3. Okay. So, is equal to 0.62 into the Peclet number based upon k and L. The parameter k in the expression for the velocity field and the total length of the plate whole to the 1/3 power. Okay. So, this is the correlation for a stagnation point flow, okay, for a flow towards a stagnation point, to find out what is the heat transfer rate under conditions of strong convection. Peclet number power 1/3, as we had expected for the flow past a rigid surface. Okay. So, I have solved for you two problems now, flow past a flat plate and flow towards a stagnation point. In both cases, the equation for the scale temperature in terms of eta is the same, and it will be the same for all problems involving a no slip condition at the surface, a rigid interface. The equation for the boundary layer thickness in terms of the streamwise coordinate depends upon the configuration and the velocity field. Using that expression for the boundary layer thickness, we can find out what is the expression for the heat flux at the surface, because we know what is dT star by d eta at the surface. We can find out the heat flux, average heat flux, and then the correlation for the heat transfer. And in all cases, it will be a constant times Peclet number power 1/3. That constant will depend upon the configuration. Next lecture, we will extend this to the flow in a pipe. Okay. In the pipe, in the case of the flow in a pipe, there is a curvature of the pipe. However, if the disturbance to the temperature is restricted to a thin region near the wall, then I can consider this to be similar to the flow past a flat plate and calculate the correlation. I will discuss that in the next lecture. I will see you then.